Hello and welcome to another Cor-Tuf video. My name is Tim and today I'm going to walk you through the production, testing, and installation lifecycle of several of our ultra-high performance concrete pilings. Originally developed by the Army Corps of Engineers, Cor-Tuf UHPC combines outstanding compressive and flexural strength with impermeable resiliency to create a product unlike any other ultra-high performance concrete of the past. One of the major differences between Cor-Tuf UHPC and other ultra-high performance concrete products is the ability for Cor-Tuf to be mass-produced using conventional, large-scale means and methods common to the concrete industry. As seen here, we're on-site at Durastress Incorporated in Leesburg, Florida. In this test, we produced two 30-foot pretension pilings and one 100-foot pretension piling. During the production phase of our testing, we wanted to prove that unlike other UHPC products, components precast using Cor-Tuf UHPC would be free of voids and would show no inward shrinking while the component cures. Working in partnership with the Florida Department of Transportation, 15 strain gauges were installed in each piling. When the pretension load at each end was released and transferred into the concrete, it was measured and, as predicted, showed no movement of the pretension cables embedded within the piling. As each piling was extracted from its form, they can be seen to be free of any voids, and aside from some slight surface staining left by the form, they were otherwise ideal. As will be seen later in the video, the surface staining was easily removed and came completely clean from the surface of each piling. In Phase 2 of our demonstration, we're on-site at the Florida Department of Transportation Structures Research Center in Tallahassee, Florida. This test will be the first of two directional pressure tests, which are designed to gauge how much stress can be imparted into a piling that is designed to withstand extreme vertical loads before it completely fails. In this test specifically, we will be applying as much horizontal pressure as possible to one of our 18-inch by 18-inch by 30-foot long UHPC pilings to gauge its complete failure point. To provide us with accurate data, strain and deflection gauges, as well as strand slip monitoring, were all used by FDOT to monitor the event. Prior to testing, FDOT had predicted a failure point of around 60,000 psi. Here we can see the flexural testing in action. At various pressure stages, the testing was paused so that the piling could be inspected by the FDOT team. Our footage of the event has been accelerated by 3,000% to help illustrate how far we were able to deflect the piling. In total, the Cor-Tuf UHPC piling was able to withstand 84,000 psi of downward flexural pressure and 4.5 inches of deflection before failing. As can be seen here, when the piling cracked, its failure point was consolidated to one area with no radiating cracks along the sides of the piling. Lastly, in Phase 3 of our demonstration, we installed our 18-inch by 18-inch by 100-foot long piling into the ground at the Lower Construction Yard in Leesburg, Florida. As was the case in our prior test, this piling was also outfitted with a full set of data capture sensors to allow us to monitor its condition during installation. The Lower Yard was chosen as the site for our installation because we had a full geotechnical report for the area prior to starting. This report would allow us to correlate our findings against the soils data for the area and present a complete picture of what was happening beneath the surface. In this test, two piling hammers were used, a D36 and a D62 respectively. We started the piling installation with the D36 hammer, as can be seen here. While installing the piling with the D36 hammer, we encountered very little subsurface resistance until we hit bedrock around the 70-foot mark. As was the case in our prior test, we have accelerated our footage of the event by 3,000% to illustrate the ease with which it initially went into the ground. Once we hit bedrock, the decision was made to see how hard and fast we could hit the piling with the D36 hammer in an attempt to cause it to fail. What we found was, instead of failing, the friction between the hammer head and the end of the piling caused the pad that was meant to cushion the blow of the hammer to catch fire and melt, as can be seen here. Due to the melting of the hammer pad from the D36 hammer and the real-time piling data report, which to this point showed no significant changes in the stress weave pattern of the piling or to its structural continuity, the decision was made to switch hammers to the larger D62 in an attempt to cause the piling to fail. Here we can see the D62 hammer in action as it continues to drive the Cor-Tuf UHPC piling through multiple layers of bedrock. Regardless of which hammer was used or how hard we attempted to hit the piling, Our data from the event showed the structural integrity of the piling never dipped below 100%. As we can see here, we eventually reached a state in which the testing crew ran out of lead length for the internal sensors, causing us to stop the test and call it a success. Lastly, this is a shot of the top of the piling after our testing concluded. Aside from the residue left by the burning hammer pad, the top of the piling is still virtually in pristine condition.